Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through the far future of the universe, past the last bright stars, past the cooling remnants of galaxies, past black holes, dark energy, and the strange question of whether time itself can still mean anything when almost nothing is left to change. This is not a journey into disaster. It is a journey into scale. The end of the universe, if such a phrase is even right, is not likely to be a single moment where everything stops at once. It is more like a long fading of possibility. Energy spreads out. Stars use up their fuel. Galaxies grow quiet. Matter itself may slowly come undone. The cosmos does not slam a door. It lowers the lights. For now, imagine standing beneath a clear night sky. The stars above you seem steady. The moon follows its familiar path. The constellations appear almost carved into the dark, as though the sky were a ceiling that has always been there and always will be. But this stillness is only the stillness of a short human life looking outward at something too large to change visibly from one evening to the next. On cosmic timescales, the universe is not still at all. It is expanding. It is cooling. It is aging. The same sky that looks permanent from the ground is part of an unfolding physical process, and every point of light in it is temporary. The first clue is written into the light of distant galaxies. When astronomers study that light, they find that it has been stretched toward the red end of the spectrum. This is redshift. It happens because space itself is expanding while the light crosses it. The farther a galaxy is, the more its light has usually been stretched, because the light has been traveling through expanding space for a longer time. Redshift tells us that the universe is not a fixed stage with galaxies moving across it like actors. The stage itself is growing. The distances between large-scale structures are increasing. A galaxy far away is not merely flying through space away from us. The space between here and there is also lengthening. That expansion changes everything about the future. Astronomers do not rely on one clue alone. The future of the universe is inferred from an evidence ladder. Redshifts, supernova distances, the cosmic microwave background, baryon, acoustic oscillations, gravitational lensing, galaxy clustering, and the growth of structure. Each method has its own uncertainties, but together they sketch the same broad picture. The universe was once hotter and denser. It expanded, it cooled. Structures grew under gravity. And in recent cosmic history, the expansion began to accelerate. This distinction matters. Observation, tested theory, model-based inference, and speculation are not the same kind of statement. We can speak confidently about expansion, redshift, the cooling background radiation, and declining star formation. We speak more carefully about exact ultra-future timelines, proton decay, vacuum decay, and whether dark energy will remain constant forever. A second clue fills the entire sky, though human eyes cannot see it. It is the cosmic microwave background, the oldest light we can observe. This radiation was released when the young universe cooled enough for atoms to form and for light to travel freely. The universe was only about 380,000 years old then, hot and dense and glowing. Since that time, space has stretched the wavelengths of that ancient light. What began as a hot glow has become a faint microwave bath only a few degrees above absolute zero. It is still everywhere, a soft remnant of the early cosmos, but it is cooling as the universe expands. The cosmic microwave background is not just a relic, it is a clock of cosmic aging. It shows that the universe has already changed profoundly, and it will continue changing. The heat of the beginning has not vanished, but it has been diluted into a whisper. It is also a map, not a photograph of stars or galaxies, but a record of tiny temperature differences in ancient radiation. Those differences are extremely small, yet they matter. They trace early variations in density, velocity, and gravitational potential, the faint ripples that gravity later amplified into the cosmic web. The patterns in the microwave background include acoustic peaks, the frozen imprint of sound-like waves that moved through the hot early plasma before atoms formed. These patterns help cosmologists estimate the contents and geometry of the observable universe within the standard lambda-CDM model. In that model, ordinary matter is only a small fraction of the cosmic inventory. Dark matter contributes much more gravitational mass, and dark energy dominates the large-scale energy budget today. This does not mean dark matter and dark energy are the same thing. They are almost opposites in the cosmic story. Dark matter clusters. It helps gravity build galaxies, filaments, and clusters. Dark energy appears comparatively smooth in the standard model, associated not with clumping, but with the accelerated expansion of space on the largest scales. So, when we speak of the universe ending, we are not only speaking of stars running out of fuel, we are speaking of a competition between gravity's ability to gather matter and expansion's ability to separate unbound regions. In the early universe, gravity had enough time and density to build structure. In the far future, accelerated expansion may isolate whatever structures remain. The stars tell the same story in another language. Every star is a temporary arrangement of gravity, pressure, heat, and nuclear fuel. A star shines because its core is hot enough and dense enough for nuclear fusion. Hydrogen becomes helium, mass becomes energy, light escapes into space. But fuel is finite. Our sun is in a long, stable phase called the main sequence. It has been shining for about 5 billion years and will continue for several billion more. That may sound almost eternal, but in the scale of the universe, it is only one bright chapter. Eventually, the sun will exhaust the hydrogen in its core. Its balance will change. Its outer layers will swell. It will become a red giant, then shed those outer layers, leaving behind a dense white dwarf that slowly cools. Other stars die differently. Small red dwarfs burn their fuel so slowly that many will live for trillions of years. Massive stars race through their fuel in only millions of years, then collapse violently as supernovae. Their cores may become neutron stars or black holes. Each path is different, but every path has an ending. The life of a star is a struggle against gravity. Gravity pulls inward. Fusion pushes outward. For a time, the two are balanced. When the fuel changes or runs out, the balance fails. This is the first great lesson of the far future. The universe does not need anything dramatic to begin its ending. It only needs every process to continue following its own rules. Behind all of this is the second law of thermodynamics. In ordinary language, this law says that energy tends to spread out. In a closed system, entropy tends to increase. Entropy is often described as disorder, But for the universe, it is more helpful to think of it as energy becoming less concentrated, less available, and less able to do work. A hot cup of tea cools in a room because heat flows from the warmer tea into the cooler air. Once the tea and the room reach the same temperature, there is no useful heat flow left between them. The energy still exists, but it can no longer drive the same kind of change. The universe is a grander version of that story. In the early cosmos, energy was concentrated in hot, dense conditions. As the universe expanded, that energy spread out. Stars formed where gravity gathered matter into dense regions, but stars themselves increase entropy by radiating energy into space. They create local islands of order by burning fuel and releasing heat. Life does something similar. A living body maintains order internally by taking in usable energy and releasing waste heat. A planet can host weather because sunlight creates temperature differences. A galaxy can form stars because cold gas can collapse under gravity. Every process that feels active and alive depends on gradients: hot and cold, dense and thin, high energy and low energy. Heat death is the idea that given enough time, those gradients disappear. The universe approaches a state where energy is evenly dispersed and no usable differences remain. There may still be particles, there may still be radiation, there may still be space. But there is no longer a meaningful way for complex change to happen. Heat death is not an explosion, it is not fire, it is not a cosmic wall. It is a leveling. To follow the path toward that leveling, begin with the age of stars. Today, the universe still contains great stellar nurseries, clouds of gas and dust where new suns are born. But star formation has already declined dramatically since its peak more than 10 billion years ago. Galaxies had more cold gas then. Collisions and mergers were more common. The universe was more active. Now the reservoirs are running down. Each generation of stars consumes gas. Some material is returned through stellar winds and supernovae, but not all of it. Some becomes locked in long-lived stars, white dwarfs, neutron stars, black holes, and planets. Over time, the raw material for new stars becomes rarer. The Milky Way still forms stars, but more slowly than it once did. Many large elliptical galaxies are already quiet, red, and old, with little cold gas left for stellar birth. They are not dead in a sudden sense. They are aging systems whose bright activity has mostly passed. In the very far future, perhaps around 100 trillion years from now, the last ordinary star will form. It will probably be a small red dwarf because red dwarfs are efficient and long-lived. It will burn faintly, using its hydrogen with extraordinary patience. Then, after even the last red dwarfs have exhausted their fuel, there will be no more starlight in the ordinary sense. No new suns, no constellations, no dawn on any planet under a living star. Imagine that future sky. Not the night sky we know with scattered points of light, but a deeper night where the galaxies have dimmed and the bright stellar age is over. White dwarfs cool into black dwarfs. Neutron stars drift as dense relics. Black holes remain as dark gravitational knots. This is sometimes called the degenerate era. The name comes from the strange quantum states that support compact stellar remnants. It is an era not of ordinary stars, but of leftovers. White dwarfs will be among the most common. A white dwarf is the exposed core of a star like the Sun, compressed into something roughly the size of Earth but with a mass comparable to a star. It does not shine by fusion. It shines only because it is still hot from its earlier life. Over trillions of years it cools. Eventually, when enough time has passed, it becomes a black dwarf, cold, dark, and invisible. No black dwarfs exist yet, as far as we know, because the universe is not old enough. The oldest white dwarfs have not had time to cool completely. The black dwarfs belong to the future, not the present. Neutron stars are stranger still. They are the collapsed cores of massive stars, so dense that matter has been crushed beyond ordinary atomic structure. A neutron star can contain more mass than the Sun in a sphere only about the size of a city. Some spin rapidly. Some send beams of radiation into space as pulsars. But over immense time, even these signals fade. Their rotation slows. Their surfaces cool. Their activity declines. Black holes, meanwhile, seem at first to be the perfect survivors. They are regions where gravity has become so intense that not even light can escape from within the event horizon. A black hole can grow by consuming gas, dust, stars, or other black holes. At the centers of galaxies, supermassive black holes can contain millions or billions of solar masses. When galaxies merge, their central black holes can eventually merge too, sending gravitational waves through space-time. In the far future, after galaxies have exhausted their gas and stars have died, black holes may be among the last large organized structures remaining. But even black holes are not eternal. They are also not simple. A black hole has entropy, and in the Bekenstein-Hawking picture, that entropy is proportional to the area of its event horizon, not the volume inside. This is one of the strangest clues in modern physics. It suggests that horizons, information, gravity, and thermodynamics are woven together more deeply than ordinary intuition expects. The horizon area matters because black holes are not merely dark objects. They are thermodynamic objects. They can have entropy. They can have a temperature. They can participate in the same broad story of energy dispersal that governs cooling stars and the approach to heat death. Stephen Hawking showed that quantum theory changes the story. Black holes should emit a faint radiation because of quantum effects near the event horizon. This Hawking radiation is extraordinarily weak for known astrophysical black holes. A black hole with the mass of the Sun would take an inconceivably long time to evaporate, far longer than the current age of the universe. Supermassive black holes would last even longer. But if the theory is right, a black hole slowly loses mass as it radiates. The smaller it becomes, the warmer it becomes, and the faster the process continues. For almost all of its lifetime, the change is nearly imperceptible. Then, near the end, evaporation accelerates. In its final moments, a black hole may release a brief burst of high-energy particles and radiation. The event horizon disappears. The black hole is gone. This is one of the most beautiful reversals in physics. Black holes begin as the ultimate form of gravitational trapping, and yet over enough time they may dissolve into radiation. The darkest objects become part of the final faint glow. Before that final black hole era, the galaxies themselves will change beyond recognition. The Milky Way and Andromeda are expected to merge billions of years from now, forming a larger galaxy. Other nearby galaxies may join. But beyond our local group, cosmic expansion will carry distant galaxies beyond our observable horizon. Their light will become more redshifted, dimmer, and eventually unreachable. Future observers, if any exist in the merged galaxy far ahead of us, may look out and see a much emptier universe. The evidence of other galaxy clusters will fade beyond detection. The cosmic microwave background will be stretched to wavelengths too long and faint to measure. The universe may appear as if the local galaxy is all there ever was. This is one of the quiet losses of cosmic time. Not only do objects fade, but evidence fades. The universe forgets how to reveal its own history. Dark energy deepens this isolation. The expansion of the universe is not merely continuing, it is accelerating. Around 5 billion years ago, expansion began to speed up under the influence of whatever dark energy is. We do not yet know its true nature. It may be a cosmological constant, an energy of empty space itself. It may be something more dynamic, but its observed effect is clear. On the largest scales, it pushes the universe toward faster expansion. The discovery of acceleration did not come from a single poetic impression of galaxies fleeing away. It came from careful distance measurements, especially Type 1. A supernovae used as standardized candles, and later from other probes such as baryon acoustic oscillations, the cosmic microwave background, and the distribution of large-scale structure. These measurements do not tell us what dark energy is. They tell us that the expansion history requires something like it in the standard model. There are active questions here. Some surveys test whether dark energy behaves exactly like a cosmological constant or whether its influence might evolve with time. Those results should be treated as an unfolding investigation, not as proof that the universe has already chosen a dramatic future. The baseline picture remains lambda c dm, cold dark matter plus a cosmological constant like dark energy, with room for future measurements to refine or challenge it. If dark energy behaves like a cosmological constant, then the far future resembles de Sitter space, a universe expanding exponentially. Distant galaxies slip beyond cosmic horizons. Regions of space become causally disconnected. No signal from beyond the horizon can ever reach the observer. In that future, even if something exists far away, it is no longer part of any reachable physical conversation. It might as well belong to another universe. This kind of expansion does not tear apart bound systems by itself. Galaxies, stars, planets, and atoms are held together by forces stronger than cosmic expansion at small scales. But on the largest scales, dark energy separates what is not gravitationally bound. It turns the cosmos into islands of causality surrounded by horizons. Here, the word horizon needs care. A particle horizon marks the limit of what light could have reached us so far. A cosmic event horizon concerns what can ever reach us in the future if acceleration persists. A Hubble sphere is something else again, not a hard wall and not the final limit of sight. These boundaries are easy to confuse because all of them involve distance, time, and light, but they answer different questions. The far future is shaped most strongly by the event horizon. It does not mean space has an edge. It means that more and more unbound regions can become permanently unable to exchange signals. The universe may continue beyond what any observer can ever know. The edge is not a wall. It is the boundary of possible contact. Eventually, after stars have died and black holes have evaporated, there may be almost nothing left inside any one horizon except extremely faint radiation, perhaps a few particles, and quantum fields in a low-energy state. What does time mean there? Time is not just a number on a clock. In experience and measurement, time is recognized through change. A clock ticks because something moves or oscillates. A planet marks a year because it orbits a star. A particle decay marks an event because one state becomes another. But if the universe becomes almost empty, cold, and uniform, there are fewer and fewer events to mark any difference between one moment and another. Time may still exist as a coordinate in the equations. The arrow of time may still point in the direction of increasing entropy. But if entropy is already near its maximum and no complex processes remain, time loses much of its practical meaning. 1 trillion years, 1 Google years, one unimaginable stretch beyond that. If nothing changes, what distinguishes them except mathematics? This is not the same as time stopping. It is subtler. Time becomes unused. There is no one to measure it, no structure to record it, no repeating process to divide it into meaningful units. The universe continues, but the story thins until narrative no longer applies. Matter itself may not survive the journey. In the standard model of particle physics, protons are stable as far as experiments have shown. But some theories beyond the standard model predict that protons may eventually decay. If proton decay is real, the half-life must be far longer than the current age of the universe, because we have never observed it. The lower limits are already enormous. Still, in deep enough time, rare events can become important. If protons decay, ordinary matter slowly falls apart. Planets, asteroids, cold stellar remnants, and every atom built from protons eventually disintegrate into lighter particles and radiation. The solid architecture of matter becomes temporary too. If protons do not decay, matter may persist longer, but not necessarily forever in recognizable forms. Quantum tunneling, gravitational interactions, and rare collisions can still transform remnants across staggering timescales. Black dwarfs may occasionally collide. Compact objects may be scattered by gravitational encounters. Even stable matter becomes subject to the patience of probability. The far future is a place where almost impossible events become possible simply because there is so much time. This is one reason the end of the universe is difficult to imagine. Human intuition is built for days, seasons, lifetimes, and perhaps historical centuries. But cosmology asks us to think in powers of 10. The lifetime of a red dwarf may be trillions of years. Black hole evaporation may require numbers so large that writing them out becomes almost meaningless. The decay of matter, if it happens, may occur on still greater scales. At such scales, the difference between unlikely and inevitable begins to blur. An event that would never happen in the lifetime of a civilization may become routine in the lifetime of the cosmos. It helps to pause inside that idea before moving on. A human life is short enough that almost every important change has a story shape. A seed becomes a tree. A child becomes an adult. A city rises, changes, and leaves ruins. Even a mountain range, if we stretch our thought far enough, can be imagined as something lifted by tectonic motion and worn by erosion. But the far future of the universe stretches beyond story. It is not only long, it is long in a way that erases familiar categories. When a white dwarf cools toward blackness, there may be no nearby observer, no sunrise, no seasons, and no dramatic event to divide one age from another. The change is real, but it is almost without texture. This is why cosmic endings often sound paradoxical. The universe is full of events now because the conditions are uneven. Matter is clumped. Stars are hot. Space is cold. Gravity gathers. Radiation flows. But the future we are tracing is a future where unevenness is slowly spent. The bright universe is a universe of contrasts. A star shines because its core is different from the space around it. A planet has weather because one place is warmer than another. Chemistry happens because particles can exchange energy in useful ways. Life is possible because energy arrives from the sun in a concentrated form and leaves Earth as lower energy infrared radiation. Everywhere there is activity, there is a gradient. The long future is the loss of gradients. Not all at once, not evenly. Some regions remain active longer than others. Black holes persist after stars are gone. Red dwarfs outlive massive stars. Cold remnants can remain for durations that make the present age of the universe look like the first moment of dawn. But the overall direction is the same. Differences flatten. Structure thins. Opportunities for change become rarer. Consider the planets in that far future. Many planets will not be destroyed by dramatic impacts or swallowed by stars. Some will be, of course. Earth itself is likely to face a difficult future as the sun brightens and later expands. But countless worlds around red dwarfs may orbit for trillions of years. Others may be thrown into interstellar space during close gravitational encounters, becoming rogue planets wandering without a star. A rogue planet is not nothing. It may carry heat deep inside for a time. It may have a frozen surface and a hidden ocean. It may drift through interstellar darkness with no sunrise and no sky of familiar constellations. But over immense time, internal heat leaks away. Radioactive elements decay. Tides weaken unless another body keeps them alive. The planet becomes a colder and colder memory of its own formation. Even worlds that remain bound to stellar remnants face a quieter future. A planet orbiting a white dwarf may circle a fading ember. A planet around a black dwarf, if such a system remains stable, receives essentially no starlight. Its year may continue. Its orbit may remain mathematically elegant. But the ordinary conditions that make geology, climate, and biology active are gone. In this sense, the end of the universe is also the end of environments. A living world is not just a ball of rock. It is a set of flows: light, heat, chemistry, atmosphere, oceans, interior motion, and time. Remove the flows and what remains may still be a planet, but not a world in the living sense. The same is true for galaxies. A galaxy is often pictured as a frozen spiral, but a living galaxy is not frozen. Gas falls inward, stars form, massive stars explode, metals enrich clouds. Stellar winds push matter into new shapes. Spiral arms are not solid structures, but moving density patterns. The galaxy breathes through cycles of collapse, fusion, death, and recycling. When star formation ends, the galaxy becomes more like an old city with no new lamps being lit. The structures remain for a while. Orbits continue. Compact remnants pass one another in the dark. But the active cycle has stopped. There may still be rare flashes. Two white dwarfs can merge. A star remnant can pass too close to a black hole and be torn apart. Objects can collide after long gravitational dances, but these events become isolated sparks in a universe where the fire has mostly gone out. This is an important distinction. The far future is not perfectly empty immediately after the last stars die. It is not a clean cut from light to nothing. It is a long tale of rare events. The universe becomes quiet before it becomes nearly silent. In that long quiet, gravity continues to do subtle work. Gravity never entirely gives up while mass remains. In dense stellar systems, close encounters can fling objects outward or pull them inward. Over very long times, galaxies can evaporate dynamically, not by heat, but by gravitational interactions. Some remnants gain speed and escape into intergalactic space. Others lose energy and fall toward the center, where a black hole may wait. The final arrangement of matter is therefore not simply a frozen museum. It is a slow sorting. Some objects are swallowed by black holes. Some are expelled into emptiness. Some orbit for spans so long that the orbit itself becomes a kind of lingering memory. The largest black holes will likely dominate the later universe. Supermassive black holes at galactic centers grow through mergers and accretion, but once the surrounding fuel is gone, they too become isolated. They no longer blaze with bright disks of infalling gas. They no longer power quasars. They sit in darkness, defined not by visible light, but by gravity and horizon. It is tempting to imagine black holes as holes in space, but they are not empty tunnels. They are regions where space-time has been curved so severely that paths leading inward cannot turn back outward once they cross the event horizon. The horizon is not a surface you could touch. It is a boundary in causality. Inside it, all future-directed paths lead deeper in. For a long time, black holes appear to be one-way endings. Matter falls in. Light cannot escape. From the outside, the black hole is described by only a few properties: mass, spin, and electric charge. The detailed complexity of whatever formed it seems hidden. This is why black holes raise such deep questions about information. Quantum mechanics suggests that information is not simply destroyed. Classical black hole physics seems to hide information behind a horizon. Hawking radiation complicates the question further, because if a black hole evaporates completely, what happens to the information associated with what fell in? This black hole information problem remains one of the great unresolved questions in theoretical physics. For tonight, we do not need to solve it. It is enough to notice that even the far future is not intellectually empty. The last black holes are not only physical remnants. They are also reminders that our theories still meet at unfinished edges. And yet, from the point of view of cosmic fate, the broad outline remains. If Hawking radiation is correct, black holes do not last forever. The timescale is almost beyond language. A stellar mass black hole would take far longer than 1 trillion years to evaporate. A supermassive black hole could last for around 10 to the 100th years, depending on its mass. These numbers do not behave like ordinary quantities. They are not just large. They are so large that the current age of the universe is effectively zero beside them. During almost all of that time, the black hole changes with unbearable slowness. It is colder than the cosmic background for much of cosmic history and may absorb more radiation than it emits until the universe cools enough. But eventually, as the background fades and the black hole loses mass, evaporation becomes the dominant direction. Near the end, the black hole's temperature rises. Its remaining lifetime shortens. The process that was once slower than imagination becomes sudden by comparison. The final burst is not the dramatic destruction of the universe, only the disappearance of one of its last strong structures. After the last black holes evaporate, what remains depends on the details of particle physics and cosmology. There may be photons stretched to enormous wavelengths. There may be gravitons, if gravity is quantized in that way. There may be neutrinos, electrons, positrons, or other stable particles. There may be dark matter particles, if they are stable. Or dark matter itself may have decayed long before. The answer is uncertain because the far future depends on physics we do not fully know. We do not know whether protons decay. We do not know the exact nature of dark matter. We do not know whether dark energy is truly constant. We do not know how quantum gravity behaves in every extreme. But uncertainty in the details does not erase the direction. The large-scale story still leans toward dilution, cooling, isolation, and loss of usable energy. Even the cosmic background radiation continues its retreat. Today, it is one of the strongest pieces of evidence for the hot early universe. In the far future, it will be stretched to wavelengths so long that it becomes effectively impossible to detect. Any observer who arises too late may have no access to the evidence that taught us the universe began in a hot, dense state. That thought is strangely moving. Knowledge has an era, too. There is a time in the universe when the evidence is available. There is a time when galaxies can be seen beyond our own. There is a time when the cosmic microwave background can be measured. There is a time when stars can illuminate the chemical history of matter. We live in such a time, not only the age of stars, but an age when the universe is still legible. In the far future, the cosmos may become harder to read. Horizons hide distant structures. Background radiation fades, stars die. The clues grow faint. Physics remains true, but the evidence accessible to local observers becomes poorer. So the bright era is also an era of memory. The universe can be studied now because enough of its past still reaches us. Light from distant galaxies crosses space. The cosmic microwave background surrounds us. Ancient stars carry chemical records. Supernovae mark expansion. The universe is not only existing, it is still telling its story. Later, that story may be muffled by expansion. This gives the present a quiet significance. We are not at the center of the universe, and we are not at the final chapter. But we are here during a rare observational window when the cosmos is old enough to contain complex structure and young enough for its history to remain visible. The heat death scenario is the most widely discussed because it follows naturally from expansion, entropy, and the observed acceleration of the universe. But it is not the only possible ending. Even heat death should be spoken of carefully. It is not guaranteed in every possible cosmology, and it is not a fire, a freeze in the ordinary weather sense, or a single final event. It is an approach toward a condition where usable free energy gradients become scarce or absent. Energy may still exist, but without useful differences, it resembles a battery whose two terminals have reached the same potential. There is no helpful voltage left to draw from. One alternative is the Big Rip. This depends on a hypothetical form of dark energy called phantom energy. In ordinary accelerated expansion, bound structures remain intact. But if dark energy grows stronger over time, the expansion could eventually overpower every binding force. First, galaxy clusters would be pulled apart, then individual galaxies. Later, solar systems would become unbound. Planets would drift from stars. As the rip approached, even stars and planets would be torn apart. In the final moments, molecules, atoms, and nuclei could be unable to hold together. The Big Rip is not currently the favored outcome because observations do not require phantom energy. But the idea remains physically meaningful enough to study. It shows how much depends on the true nature of dark energy, a component that dominates the universe's energy budget and yet remains deeply mysterious. If heat death is a fading, the Big Rip is an unraveling. The universe does not cool into stillness. It stretches until structure itself cannot survive. Another possibility is vacuum decay. This is stranger than the Big Rip because it does not begin with stars, galaxies, or expansion. It begins with the vacuum itself. In quantum field theory, empty space is not truly empty. It has fields, properties, and an energy state. It is possible in some models that our universe sits in a false vacuum, a state that is stable enough to last for a very long time, but not the lowest possible energy state. Imagine a marble resting in a shallow dip on a hillside. It appears stable because small disturbances do not move it. But if it could somehow pass through the barrier around the dip, it would roll to a lower valley. Quantum tunneling gives fields a way, in principle, to make transitions that would be impossible in ordinary classical motion. If our vacuum tunneled to a lower energy state, a bubble of true vacuum could form. That bubble would expand at nearly the speed of light. Inside it, the constants and laws that make ordinary particles, atoms, chemistry, and structure possible might be different. Everything the bubble touched would be transformed. There would be no warning, because no signal could outrun the bubble wall. One instant, the universe would continue as before. The next, the local laws of physics would be replaced. This does not mean vacuum decay is likely. The time scale may be longer than any other time scale we can discuss, or the current vacuum may be stable after all. The measurements of particles, such as the Higgs boson, place our universe near an interesting boundary in theoretical calculations, but not in a way that should be treated as an immediate threat. Vacuum decay is less like destruction and more like a change of foundation. It is the stage itself becoming another stage. There are also cyclic possibilities. Some models imagine that the universe may not have a final ending at all, but may pass through phases. In older versions, expansion slows, stops, and reverses into a big crunch. The universe collapses back into a hot, dense state, perhaps followed by another expansion. Current observations of accelerated expansion make a simple Big Crunch unlikely. If dark energy continues behaving as it appears to behave, the universe will not reverse under gravity. It will keep expanding. But more sophisticated cyclic models do not always rely on ordinary recollapse. Some propose bounces driven by quantum gravity. Some imagine higher dimensional structures whose interactions generate repeated Big Bang-like events. Some suggest that what we call the beginning was one phase in a larger process. These models are speculative. They are not established in the same way as cosmic expansion or stellar evolution. But they are useful because they remind us that the word end may be too small for cosmology. The universe may end in our sense while reality, or some deeper structure, continues in another form. The same caution applies to multiverse language. Inflation and quantum cosmology can motivate ideas about regions beyond our observable universe, But those ideas are not the same as mapped territory. Observations constrain our patch. They do not reveal the total extent of all space. A nearly flat, observable universe does not prove that the entire universe is infinite, and a horizon is not proof of a physical border. So the safest path is humility. The observable universe has a history we can study. It has an expansion we can measure. It has patterns in the microwave background, large-scale structure, supernova distances, and galaxy surveys. Beyond that evidence, imagination may continue, but it must walk more softly. To see why this matters, return for a moment to the human habit of storytelling. We like endings that answer beginnings. A seed becomes a tree. A journey reaches a destination. A question receives a reply. But the universe may not be arranged for narrative satisfaction. It may have laws, not closure. Heat death is unsatisfying as a story because it has no final scene. There is no last trumpet, no collapsing curtain. There is only decreasing possibility. The end is approached asymptotically, meaning the universe moves closer and closer to a final condition without necessarily arriving at a single marked instant. The Big Rip is more dramatic, but less certain. It gives us a final event only if dark energy behaves in a specific and currently unconfirmed way. Vacuum decay gives an even sharper transition, but one that may never occur and could be so far removed from ordinary cosmic evolution that it belongs more to the foundations of field theory than to the life cycle of stars. Cyclic models offer renewal, but at the cost of deep speculation. They invite us to imagine that what looks like an end from inside one cosmic phase may be part of a larger rhythm. Yet without direct evidence, they remain possibilities rather than conclusions. So the honest answer is not a single fate spoken with perfect certainty. The honest answer is a landscape of possible futures, with heat, death, and continued expansion currently among the most natural interpretations of what we observe. Still, even uncertainty has a shape. We know stars are finite. We know the cosmic microwave background is cooling. We know star formation has declined from its ancient peak. We know expansion is accelerating. We know entropy increases in physical processes. We know black holes are tied to deep questions of gravity, thermodynamics, and quantum theory. From these known pieces, the far future begins to emerge. It is a future of less light, less heat contrast, less reachable matter, less structure, less change. But less is not the same as meaningless. The universe has already created complexity beyond anything the early hot plasma could display. It made atoms, stars, heavy elements, planets, oceans, clouds, cells, minds, instruments, equations, and questions. The fact that complexity does not last forever does not make it an error. It makes it an interval. And intervals can matter. Think of a note played on an instrument. The note begins, it resonates, it fades. Its fading is part of its nature, not a failure of the sound. The universe's bright age may be like that, not permanent, but resonant. Not eternal, but real, while it lasts. The far future also changes how we understand calm. At first, the end of everything sounds frightening because it seems to erase the familiar. But the more slowly we approach it, the less it resembles catastrophe. It becomes a study in impermanence at the grandest scale. Even galaxies are temporary arrangements. Even black holes have lifetimes. Even time, in its useful measured sense, may depend on there being events to count. Nothing in this view asks us to be afraid. It asks us to be precise. The universe is not ending tonight. It is not ending tomorrow. The timescales involved are so vast that all human history is a spark inside the opening movement. The stars are still young enough to shine. The cosmic web still stretches across the observable universe. New stars are still forming. Planets are still orbiting. Light is still arriving from distances so great that it began its journey before Earth existed. What the far future offers is perspective. It reminds us that permanence is not the measure of value. It reminds us that the present age is not ordinary merely because we are used to it. It reminds us that a night sky full of stars is not the default condition of reality, but a phase in the life of the cosmos. For countless future ages, there may be no such sky. And so the sky we have becomes more astonishing. There is a philosophical softness in that uncertainty. Heat death, big rip, vacuum decay, cyclic renewal. Each future changes the meaning of ending. In one, the universe remains but loses activity. In another, structure is torn apart. In another, the laws change. In another, endings become transitions. What all of them share is that the present universe is temporary in its current form. The age of bright stars will pass. The galaxies will not remain as we know them. The cosmic microwave background will become undetectable. The night sky, if any observer could see it, would become emptier and darker. Matter may decay. Black holes may evaporate. Horizons may isolate every remaining region from every other. The universe we inhabit now is not the final state. It is a brief, luminous interval. That might sound lonely, but it can also be grounding. We live during the stelliferous era, the age of stars. This is the time when the universe has enough structure and energy contrast for galaxies, planets, chemistry, and life. It is the time when the elements forged in stellar cores can gather into worlds. It is the time when a mind can look up and ask what happens next. You are made of matter that belongs to this bright interval. The carbon in living tissue was formed in stars. The oxygen you breathe was shaped by stellar processes. The iron in blood traces back to violent cosmic events. Your body is not separate from the universe thinking about its own future. It is one of the ways the universe briefly becomes aware of scale. Even that familiar phrase, that we are made of stardust, deserves a gentle correction. Many elements in our bodies were forged by stars and stellar explosions, but much of the hydrogen in us is older than the stars themselves. It reaches back toward the early universe, so you are not only made from the ashes of stars. You are also carrying some of the simplest matter from the universe's first chapters. The eventual darkness does not erase that. If a candle burns for one evening, its light is not meaningless because night follows. If a star shines for billions of years, its finitude does not make it less real. The same is true for the age of galaxies, for planets, for life, and for thought. The future stillness of the universe does not diminish the astonishing fact that for a time the universe is awake enough to wonder. Hypnos moves gently through that thought, not as a warning, but as a guide. The far future does not need your worry. It is governed by equations, fields, gravity, expansion, and time. It will unfold on scales beyond any human obligation. The stars above you tonight are temporary, but they are here. The warmth of the present universe is temporary, but it is real. The cosmos is moving toward conditions beyond our imagination, but it has not reached them. We live in the chapter of light. So let the great future remain where it belongs, far beyond the horizon of ordinary concern. Let the dying stars, evaporating black holes, and silent fields become not a burden, but a measure of how wide existence is. The universe has room for beginnings, endings, and long, quiet transitions between them. At the edge of thought, the final question remains open. Does the universe end, or does it merely become unrecognizable? Does time stop, or does it continue without events? Does matter vanish or change into forms no memory could hold? Does the cosmos close or breathe again through some deeper cycle? We do not know. But we can say this: the universe is not static, it is a process. It began hot and dense, grew vast and structured, made stars, made elements, made worlds, and in at least one small place, made observers who could ask about the end. And perhaps that is enough for tonight. The last stars are not fading yet. The galaxies have not gone dark. Black holes still wait in the deep centers of things. The cosmic background still whispers through space. Time still has events to carry. Light still crosses the dark. For now, the universe continues. Hypnos closes the door softly behind the thought. Beyond it lies the far future, patient and immense. Here, in the present age of stars, nothing more is required than quiet attention to the wonder that we are here before the final silence.